Here we are rounding out the antenna parameters material with an example. We're going to take the Hertzian dipole through the paces and calculate some of the different antenna parameters. And just to recap, we start with the current model that had some delta functions in it for the Hertzian dipole, but it'd be different for other antennas. Then we go from there to the far electric field. The magnetic vector potential is part of that step. I'll put a far in here just to remind ourselves we're talking about the far field. Then what we do is we calculate the power density, time average power density, and from that we get all the different antenna parameters. So we're going to go through that process for the Hertzian dipole. The power density that we calculated was r hat and some constants. And that would be watts per meter squared for the units. Okay, so what do we do first? Well, the first thing is to get the radiation pattern. The radiation pattern F is equal to S over S max. So S without the vector decoration on top just means the magnitude of the vector quantity. Sometimes we'll call that SR because it's in the radial direction. So I look at what I had for S, I find out the maximum value would of course be where sine squared theta is 1. So I put that in the denominator, eta over 2 KIL or 4 pi r squared. Just to be quick in writing, I'm leaving out some of the subscripts. On the top, we have the same thing, KIL over 4 pi r quantity squared with the sine squared theta. And you can see that everything cancels except for the sine squared theta. And that highlights an important property of the radiation pattern. With the radiation pattern, we're really just trying to isolate the angular dependence. For a more complicated antenna, there'd be a function of phi in there as well. And then just by convention, we normalize the radiation pattern so its peak value is 1. And that is what we have here. Okay. Now we want to plot that and take a look at it and try and understand what's going on. So we'll look at that in the XZ plane. And I want to do a polar plot. And that will be as a function of angle, theta, down from the z-axis. So to do a polar plot, we rotate that angle theta and then put a point equal to the value of sine squared theta. At theta equals 0, we have 0, so we start there. As theta gets bigger, sine squared theta grows until it becomes 1. It's 1 when theta is all the way down at 90 degrees, and then it goes back down, and the plot repeats on the other side. Now, I've only plotted one cut, an XZ plane cut of the pattern in 3 dimensions. The pattern is rotated. It's kind of like a balloon. It's sort of squished in the middle. It's hard to draw, but it kind of has the same cross section at all angles. And the point of that is no power goes in the vertical direction. Power radiated by the dipole mainly goes out in the azimuthal directions, out at 90 degrees from the z-axis. Okay, next thing we want to do is get the beam width. The null-to-null beam width is easy. We go from straight up to straight down. So the theta null-to-null beam width in this case is pi or 180 degrees. Okay, the 3dB beam width is usually more important than the null beam width. So what we want to do is we want to go down to the angle where the value is equal to 1/2 of the peak value. So we set sine squared theta equals 1/2, and the theta that comes out of that is 45 degrees. Now the null-to-null beam width is from the one 3dB point to the other, where we're 3dB down or half in natural numbers. So we have to take the theta equals 45 degrees, which is here, subtract it from 90 to get this 45 degrees. And we have 2 of those because we're going from from one 3dB point to the other. So the half power beam width is equal to 90 degrees. So that's a measure of the width of the main beam. We go from one half power point to the other. Now that is a very low directivity antenna. The main lobe is broad, and that arises because we have a wide half power beam. That's because the antenna is small. Okay, so a little bit on the radiation pattern. There are no side lobes for the Hertzian dipole. More complicated antennas will have side lobes in the pattern that also represent radiated energy, but not as strong as in the theta equals 90 degrees that we have for the Hertzian dipole. Okay, so now let's get a little more space. The next thing we want to do is integrate to get the total radiated power because we need that for directivity and gain. So we're going to do a double integral of the average power density, r hat, r squared sine theta, theta, d theta, d phi. And again, this is watts per meter squared, which we're integrating over meters squared. Radiated power is a power in watts. It's not a power density. So we're going to plug in for that. And I'm going to put the constants out in front just to sort of get them out of the way. And then I'm going to put in the limits for the integration over a full sphere. This is a closed integral over a sphere surrounding the antenna. Phi is going to go from 0 to 2 pi, and theta is going to go from 0 to pi. And then I have a 1 over r squared from the S average, and a sine squared theta also from S average. And then from the differentials, I have r squared sine theta d phi, and the r squared in the differential cancels with the 1 over r squared in the power density. And now we're ready to work some integrals. The phi integration, since there's no phi dependence, just gives us 2 pi. So I'll have 8 over 2, the same thing squared, 2 pi. And then for the theta integration, I have sine cubed theta. And that we can do with calculus rules or table lookup or on a calculator, but that integral happens to be 4/3. So putting that all together gives me eta k I naught L over 4 pi quantity squared times 8 pi over 3, or a little bit of further algebraic simplification, eta k I naught L squared over 12 pi. And that is the power in watts radiated by Hertzian dipole. Now notice that depends on both the frequency and the length of the antenna. It certainly depends on the current we put in. The more current we put in, the more power we radiate. But the frequency and the length dependence, that will come back a little bit later. Okay, now we're ready to get the directivity. Directivity is S max over P rad over 4 pi r squared. In other words, the power density of the dipole divided by the power density of an isotropic antenna, which radiates the same amount of power but spread evenly over a sphere. We're going to get eta over 2 KIL over 4 pi r all squared. The sine squared theta maximizes at 1. Then I put in the eta, and then KIL squared over 12 pi. And then there's an over 4 pi r squared. A lot of things are going to cancel. The etas go out. The r's go out. The KIL squareds go out. And what's left is there's a pi's also go out, so we get a 12 times 4 over 2 times 16, just combining all the constants, moving some things into the numerator. In the end, that reduces to 3/2 or 1.5. So that is the directivity of the Hertzian dipole. Again, that's a fairly low directivity. Incidentally, the directivity of an ideal isotropic antenna is 1, as can be easily shown from the definition. Okay, now we need to introduce another concept. We have the let's see, radiation efficiency. The radiation efficiency for the Hertzian dipole, since it's a very simplistic model, happens to be equal to 1, in which case the gain is also equal to 3/2 or 1.5, because this is a lossless model. If we wanted to include loss, we'd have to have a more complex model for the antenna, and then that would reduce the radiation efficiency, and gain would be a dB or 2 or more lower than the directivity. Okay. The last thing we want to do is we need to get the radiation resistance, and we do that using 1/2 I naught squared r rad. That comes from the T-line side of the antenna, and from the radiation side of the antenna out into space, that's equal to the radiated power. which is the KIL squared over 12 pi, and then an eta. And if we do some algebra on that, we find that the radiation resistance is equal to eta KL squared over 6 pi. Okay, so now let's run some numbers. If the length of the antenna is lambda over 2, then KL is 2 pi over lambda times lambda over 2, or pi. That should be reminiscent of the beta L's we had in transmission lines, same idea there. If we plug in and run the numbers, this is about 377 ohms in free space. What we get is R rad for the half wave case is 200 ohms. And now we have to remind ourselves of the fact that the Hertzian dipole is a very simplistic model. In fact, what we did is we modeled the current on the antenna, plotting the current as a function of position as a constant. So this is the current as a function of z along the wires, and this is the z direction. Well, that's a very simplistic model because it ignores the fact that the current has to go to 0 at the ends of the wires. So we use a more accurate model called the sinusoidal current model. Now that's still approximate, but it's much more accurate. Now, what we got for the half-wave dipole case, L equals lambda over 2, for the Hertzian dipole model was R rad equals 200 ohms, and the directivity was 1.5. On the sinusoidal current model, if you look at the lecture notes, that's covered there, and the derivations all worked out. What we get for the radiation resistance in that case is about 73 ohms, and the directivity is equal to 1.6. Okay? Now, that's just a better model for the current, so we get more accurate values for the directivity and radiation resistance. The directivity isn't that different. Hertzian dipole works about as well as the sinusoidal model. But the radiation resistance, which controls the power radiated by the antenna, which is really important in applications, we get a better value. Now we can go one step further. We get a current that kind of looks sinusoidal, but it's a little maybe flatter and steeper. And we do that with a numerical model. In other words, we use software, an algorithm to find the current, and that is a graduate level topic. Writing the codes, finite difference, finite element, method of moments, and all some very sophisticated codes for modeling this antenna as well as many hundreds of other antenna types numerically. In fact, in our research, we created a model of the Arecibo telescope, which has a 300-meter dish. It has a secondary reflector, tertiary reflector with a real custom designed shape, and we have a full numerical model for the whole system, all designed to model that as an antenna in the same way we're doing here. We model the current, we get the radiated field, and we compute the antenna parameters from that. Needless to say, the gain of the Arecibo antenna is much higher than 1.5 for the Hertzian dipole. So that concludes our consideration of the Hertzian dipole example, and it shows you how to get some basic antenna parameters for a very simple antenna example.